And the first presentation we're going to hear from is from Nolan Pearce, KE8JCT from West Point, and it's Direction Finding, Analog and Digital Applications.
This is Radio Direction Finding, Analog and Digital Applications for HamSCI 2020 by Cadet Nolan Pearce, KE8JCT. My poster introduces the concept of radio direction finding and discusses both its analog and digital aspects. So what is direction finding? It is a hobby activity just like moonbounds or QRP, occurring primarily in the VHF band. In scheduled events called fox hunts, one ham will transmit on an agreed frequency from an unknown location. Other hunters use RDF tactics to find the location of the signal. First and probably easiest is analog direction finding. Analog hunters use only directional antennas like beams or Yagis and rotate their antennas to hear the signal gain and lower in volume. So for example, here's a Cadet Amateur Radio Club W2KGY in the middle left picture. And we're armed with our PVC tape measure antennas, so they were incredibly cheap and homebrew. Below is an antenna gain plot on EasyNet for a 3-element 2-meter antenna. And when we direction find, we're keeping this gain plot in mind. So when we're at 0 degrees to the signal, we hear a peak. And then as we rotate 90 degrees, we'll hear a null. So we won't hear the signal well at all. 180 degrees, we're going to hear it slightly better. And so we will physically rotate our bodies until we hear the signal in the strongest strength. And then we assume that to be 0 degrees, and then we continue from there. So DFers also attenuate their signals by removing antenna elements. For example, to have increased selectivity on their signal. So in our fox hunt, all we would do was take an element off of our PVC antenna, and then we'd have greater selectivity over our signal. So we'd be able to hear the peaks and nulls much clearer. So the equipment is very low cost, and it's usually homebrew with analog direction finding. So it's very responsive, but only gives bearing signals, nothing like the GPS location of digital direction finding. Digital direction finding produces a higher yield of information at a greater cost of knowledge with signals. With software-defined radios, you can get GPS coordinates of your signal. Further, many software programs like MATLAB and GNU Radio allow for the identification, retransmission, and demodulation of captured signals. So here's an AM signal demodulation in MATLAB. In the blue and in the light orange is an AM signal, so that's, of course, amplitude modulation. It has a carrier frequency and then a message frequency. So in MATLAB, I was able to capture an AM signal and then demodulate it to just the orange signal, which is my message frequency, which is a sinusoid. And that could be speech, or that could be a digital transmission also. Digital direction finding and signal intelligence is an ever-increasing industry, but sometimes cannot be beaten by its immediate response analog counterpart. So here's a Kerberos SDR at the image below. The Kerberos SDR is 4 RTL SDR dongles that are clocked synchronously, allowing for a direction finding array. And it is $150, but you are able to get GPS coordinates from a signal that you transmit, which is really impressive on a VHF band. And this is from its Android app, which is it gives you a compass bearing of your signal. So the equipment is usually high-cost SDRs. So the Kerberos SDR, Packard F1 is used more for signal identification, but it used a lot in demodulation. And then digital signal processing software, so like MATLAB or GNU Radio. So you can do all sorts of cool things with digital direction finding. It gives a bearing, a GPS location, and the ability to decode and manipulate signals within the SDR software. So you can do all these things requires a lot of knowledge on your software and a lot of knowledge on your signal. And if you're trying for the same result of just direction finding a signal, maybe your analog direction finding would be better because maybe you only need a bearing and not a GPS location. So I hope to explain both the differences in the analog and digital aspects of radio direction finding. Thank you.
All right, we'll open it up to questions.
This is N0AX. I was interested in how you generate the direction of arrival. There was a little graphic down at the bottom right of your first slide about that. How do you do that? I think that'd be pretty cool.
Good afternoon. My name is David.
Yeah, so we use the Kerbos SDR. So that's for those little RTL SDR dongles, and they're all clock synchronously. So direction of arrival, we set it up in a uniform circular array. So each of the figures are arranged in a circle. It'll take, you can use radar, you could use just regular DOA, which is what the Kerbos SDR does. So it'll receive one signal and then calculate the time difference of arrival to the signal next to it. And I think that's how the Kerbos SDR works. And then so it's very buggy on my phone right now, but it is able to give you a GPS location in the VHF band. So we use the regular Fox Hunt frequency. We took this up on the roof at West Point. We had a lot of interference with metal bouncing around, but we were able to get like a pretty accurate bearing.
Oh, okay, that's interesting to me. How big was the array? How far apart were the elements?
Yeah, so they recommend, so we had it for 2 meters. They recommend about a third element spacing in between in your circle. But then it uses an algorithm called music for the direction finding. And you'll find that's in like the Edis SDR. It also uses music. That's more widely accepted than just an app. So there's different spacing that's recommended per frequency. So a third element spacing, while it's recommended for just in general, it's actually best for the 70 centimeter band, which is what we found. So we're going to continue. This is a senior at West Point and I that we're working on. Continue trying to find what frequency is best for what element spacing.
Okay. The reason I'm asking is I've been trying to get some of the robotics people interested in a drone-based direction finding contest where either you would fly it around and look at a direction of arrival and fly it, manually, or you could do it in an autonomous mode and have the drone itself carry the computing platform to find the hidden transmitter. So this is of interest, I'll put it that way.
Yeah, so with the drone thing, that's actually what our prototype was, because music works really well with random spacing as well. And then the drones they can just spread out to whatever element spacing you want. So that was our prototype, was actually going to use drones flying in the air with antennas on them to space out.
Okay, pretty cool.
Yeah.
It's almost like I'm thinking it has pay-per-view potential there.
Yeah, definitely.
That is pretty cute. Congratulations on the work. Congratulations on getting the West Point ham station up and running. And I like that of being able to remove the director from the tape measure beam to reduce directivity and reduce sensitivity when you're close to the target. I don't think I'd seen anybody do that before. So we will have to give that a try at our next Fox Hunt. Good job.
Yeah, we beat all the people with the $1,000 rotatable Yagis because we had our little tape measures. The signal was so strong in the beginning that the only way to find it was with attenuation. So one of our new hams who had his license for about 2 weeks just took an end off of the PVC pipe, and then we found it from there.
So what's the antenna array that you were using? You called that DOA?
Yeah, so that's direction of arrival. And then I don't have a picture with me now, but we made our own. It was 4 2-meter dipoles kind of arranged in a circle. And we use that for the Kerbos SDR.
And what
the
was
Army has one. The Army has one called the Watchdog, I believe. And so it looks like it's a man pack for 2 meters. It's really interesting.
Now, are you switching them or running into 4 channels?
It's 4-channel SDR.
Got it.
The older technique was the synthetic Doppler where you're switching them using an FM detector.
Right, yep.
And that works well. There's Coast Guard literature of that back to the 50s.
Right. There's a book called Radio Direction Finding, or Transmitter Hunting, Radio Direction Finding Simplified. And that's published in about 1986. And that's got a lot of information. Coast Guard Auxiliary, the Easy Flyer, and all these different, very outdated direction finding techniques.
Now, how is it getting a GPS location off of a single direction?
So that's a really good question. That's still really experimental. Most of the time it'll crash our app. You have to have the VHF signal a really long distance away. And then I imagine it'll input from the signal strength that it receives. Because that is an option that you put is the bandwidth of the signal. is an option that you put into the app. So it must be how much it peaks on the bandwidth. And then it sees like this far away for your selectivity.
It must be calibrated to a particular transmitter then.
Yes, yeah, it's calibrated to a bandwidth, a frequency, and then you input each of your antenna's gain options. So how much gain each of your antennas have.
It would seem that would give you azimuth by just looking at the relative strength by rotating your antenna, electrically rotating it off of the azimuth. Basically, you're sweeping like a Doppler scan and looking for signal strength, right? So that gets you azimuth, but how do you get distance?
Yeah, that's definitely a really good question. I'll have to check with the people who made it. It was on Indiegogo, so it's still kind of experimental. But in the video that they use as a demo, they have people driving around looking at their GPS location. It looks really similar to how the Kiwi SDR does it, where they have a lot of different plots at where the signal may be, and then they have kind of a heat map.
Might they have two? Might they have had two people, two different locations?
No, I don't believe so. That would be good. That's like time difference of arrival.
You know, we do DFing around here for fun and not so fun. And you usually have to have two people coming up with a direction.
Mm-hmm.
Then you find where they cross.
Yeah.
Got about 5 minutes if you want to ask some more questions.
Yeah,
I just
Nolan, I just want to say sorry we didn't get together when you were out here. It was a pretty busy time for me.
Yeah, no, that's fine. I brought my APRS handheld when I was biking around. So I was in the Tempe area.
Yeah, I was watching you bike around.
Yeah.
Yeah, I just wanted to add that you mentioned the Watchdog. The Watchdog's the HF-DF system, and it's not really Army equipment, I guess, but we're testing that. But there's also the VROD VMAX system is a tactical system that is a backpack system, and it's kind of similar to the Kerberos SDR, but I think it's made with GNU radios, or I mean with USRPs, and it does the same idea of the clocked SDR, so that it doesn't do like a radar. It does just the measuring of each individual signal instantaneously. I believe that way finds a more instantaneous direction than the radar does, just because of the way that works.
Well, you should be able to look at the basically beamform and sweep the beam across the signal, and so you can get a very accurate azimuth measurement, right?
Yeah. The Kerberos SDR also does beamforming as well. So they used it to track car traffic and then airplane traffic.
Okay.
With two separate Yagis adjacent to each other.
I should also mention that Nolan put a nice picture in the chat that you can click on of the system you were just talking about.
Looks like a 21st century Doppler scan.
Yeah.
So we would do that with just verticals on the roof of a car. We call it a four-square, and then we would think, like Ward was saying, we'd sweep them because we didn't have an SDR back then. So we just sweep them and look at relative signal strength. As we swept, we electrically rotated the array using analog circuitry, if you can believe that.
Yeah, use pin diodes to switch them.
Yeah.
Okay, any final questions?